So thanks so much for the introduction, Dan. I'm XD. I'm here to present this collaborative work with my colleagues, Yichen, Tianxing, Ruchir, and Zhou. We're all from Dartmouth. And Yichen is a postdoc at Dartmouth, but he's also the leading author of this work. But unfortunately, he cannot be here because of the visa issue, so I'm here to deliver the presentation. So what we're looking at here is basically Yichen is wearing a pair of Google Glass. He's making some mid-air swipe gestures, as well as some finger touch gestures. And we have a computer monitor showing that the system can recognize what gesture he's performing. And you must have noticed that there's a white plastic box hanging off the end of the Google Glass. And there's also a narrow plastic type of thing mounted on the side of the Google Glass at the location where the trackpad is located. If we take a closer look at it, you'll find that the narrow plastic thing is basically a grid of solar cells. And we know that solar cells is something that we can use to harvest energy and convert energy to electrics. But in this work, we propose that the solar cells can also be used as a sensor to detect touch gestures or mid-air finger gestures. So here's a little bit of a sensing principle. And what I'm looking at here is we have two solar cells in the figure, and the solar cells can harvest energy from indoor and outdoor lightnings. And if I have my finger moving from right to left, and my finger is going to hover above one of the solar cells, which may create some light blockage, which may introduce a drop in the amount of energy that is harvested by that particular solar cell, representing by the dip on the top left corner of this slide in the blue line. And if I keep moving my finger to the left, so my finger is going to hover another solar cell, which may cause a dip in the green line. So based on this temporal information, we should be able to figure out what gesture actually the user is performing. So in order to detect this drop in an amount of energy that can be harvested by the solar cell, we use a fairly simple a threshold method. It's a dynamic threshold method called a constant false alarm rate, which is popularly used in radar applications. And the reason why we want to use this dynamic threshold method is because this is pretty good at against environmental noises, which is very common in outdoor environments. So what I'm looking at here is the sensors in action. We have two solar cells on the breadboard, and we have an oscilloscope showing two lines, a yellow line and a red line, representing the amount of energy that is harvested by the solar cell. And if I move my finger and hover above the solar cell, you see that the energy drops. If I touch the solar cell, you will see a drastic change in the amount of energy. So this is basically how it works. And so the entire system is composed of this grid of solar cell as well as some electronics. And we also run the gesture detection and the recognition logics on that electronics, on the MCU basically. And the system consumed fairly good an amount of power. In this particular time, when we took this photo, the system consumed about less than 40 microwatts of power, which is pretty good. But I think what's more fascinating here is that the amount of energy that can be harvested by these solar cells exceeded the amount of energy that is needed to detect and recognize what gesture the user performed. And at this particular moment, we took this photo in an indoor lab environment. This grid of solar cell can harvest 68 microwatts of power, which means that the system can run and detect, recognize finger gestures without the need of an external battery. So the motivation of this work is definitely, recent years we've seen increasing amount of wearable devices, small devices, and small IoT devices. And one of the sort of like challenges for these devices to become even more popular is the battery, right? We do not want to charge these devices once per day. In many situations, we want to charge them perhaps only once per lifetime. So this is the reason why recently we've seen a line of very, very cool, interesting projects in this field of batteryless devices. If you look at the left one, you see that this is a batteryless phone, and the one in the middle is just a batteryless screen, and the one on the right, middle, left. The one on the left is the is the batteryless camera. But within the existing literature, there's no devices allowed the user to perform input or touch input, immediate touch input, without the need of a external battery, and this is exactly what we're doing here. And we've created two prototypes, one in the smart glass form factor, another one in the smart watch form factor. But please understand that this technology can be used in many other small devices, like IoT devices. So this is the smart glass form factor. We have this 48 solar cells, and we've connected these solar cells to the MCU circuit, and we use the MCU to read the voltage data in order to detect whether there's a gesture or not. And then we run the gesture recognition logic also on this MCU unit. Okay? So for the MCU to read the voltage data, it takes only about 5 microseconds, which is pretty fast. But within that 5 microseconds, all the other solar cells are dedicated for harvesting energy, which means that for most of the time, the system actually is used for harvesting energy. And in order to detect and use a gesture, we run the system in about 35 hertz. And if you look closely, on the back of this MCU circuit, we also have this power management circuit, which basically deals with anything that is related to power, but with the most significant one being power harvesting. So this is how the system works. We have a number of solar cells, and then we've connected the solar cells to two circuits. One is power management circuits, and the other one is voltage reading circuits that basically deal with just the detection and recognition. And we have to switch these circuits frequently. This is why on the back of this solar cell panel, we have a number of switches and a decoder or a decomplexer. And we've also created this smart watch prototype. It's pretty much the same thing, except that we have a slightly less number of solar cells, and we have more switches and decoders. This is basically a circuit design limitation, which actually increases the power consumption, which I will discuss later. And for the rest of the part of the system, it's pretty much the same. We have microcontroller and a power management unit. So in terms of the gestures that the user can perform on these devices, very simple gestures, but they are very useful. I mean, common gestures in interacting with small devices. For example, the user can swipe forward, the user can swipe backward, and the user can tab it, can do a double tap, and 2-finger taps. And on the watch, the user can swipe right, left, swipe up, swipe down, and tap it, and double tap without tapping the screen. All right, so we've conducted a user evaluation where we recruited 10 participants, and we asked each participant to repeat these 12 gestures, and each gesture was repeated 20 times, so in total we've collected 2,400 gesture samples for analyze. So we were very interested in knowing about the gesture recognition accuracy, so we reported accuracy in two forms. One is precision, another is record. So precision represents the percentage of correctly recognized gesture among all the detected gestures. So not all the gestures can be detected. And record means that the percentage of the correctly recognized gesture among all the gestures, regardless if it's detected or not. So for both prototypes, we've got pretty good numbers. And for both precision and record, we've got numbers higher than 97%, which is pretty good. And the record is slightly lower, as you can imagine, that not all gestures can be detected. All right, so in terms of power consumption, we tested the power consumption and only when the system is running in the voltage reading mode, because in energy harvesting mode, it does not really consume much power. And of course, the video is too fast, but I want you guys to focus on this table. So 95% of the power was consumed by the MCU, and within this amount of power, if you look at the column on the left side, you'll see that the ADC, the analog to digital converter, actually consumed quite a lot of power, and the gesture recognition logic also consumes some power, and the decoder and the switches actually did not consume much power because we use very energy efficient hardwares. So on average, the glass prototype consumes about 34 microwatts of energy, but the watch actually consumes much more, almost double it up. The reason for that is pretty simple. First off, so we have more switches, we have one more decoder, which consume much power. And then also, for the watch, we have 2D gestures, so which means that the gesture recognition logic also consume more power. All right, so let's see the amount of energy that can be harvested. We've tested the system in indoor environment as well as in the outdoor environment. Because of time limitation, I'm only going to show you the examples in the indoor environment. In the indoor environment, we've tested different lightning intensities ranging from 200 to 2K lux. 200 is really, really dark. So for all the conditions other than 200 lux, we can get enough power, meaning that greater than 44 microwatts, that's greater than 34. But for 200, unfortunately, we won't be able to harvest enough power. But when I show the power management circuit, I don't know if you guys recognize, there's something that looks like a battery, but it's not a battery, it's a supercapacitor, which is something that we use to store the energy when the system is not in use. We don't want to waste energy. So in that situation, we can use the power from the supercapacitor to power up the system. And this is for the smart watch. And you may notice that for very similar conditions, the smart watches can harvest more power. We can get, for most of the situation, we can get more than 66 microwatts of power. The reason is very simple. For most of the time, because the smart watches solar cells facing the ceiling, this is where the actual light come from. And in order for the system to sort of like work in a real world situation, we have to test it in a situation where a lot of lightning noises happening. So we test the robustness of the system and in terms of different light intensity, light direction, and the fluctuation of the light, all sorts of conditions. These are in the papers. For now, in this talk, I'm just going to show you two examples. First off, we test the robustness of the system in terms of gesture recognition accuracy in different light intensity. So we've tested in an indoor environment with light intensity ranging from 200 to 1K lux. So the average precision recall are pretty good, 100%. But when we move on to the outdoor condition, you see that the percentage actually goes down a bit. 95, not too bad, but it goes down a bit. The reason is very simple, because outdoor lighting condition is uncontrolled. We have a lot of fluctuations in the natural light, and also the shadows from the moving leaves may also cause some problems. So we've tested the smartwatch prototype in these similar conditions, except that we have one more condition for the smartwatch. That is the dark room condition. It's completely dark. So the reason for that is we want to mimic the situation where people wake up at night and just want to look at the watch and maybe do some very brief, interactions. So in this particular case, the watch actually, the sensors actually detected a finger gesture based on the light emitted from the screen, and it bounced back from the finger. You can see that the precision is still pretty good, but the recall goes down a bit. We get a 90% of the recall. Simply means that the light intensity is not strong enough to guarantee that all the gestures can be detected. So what about nearby movement, right? We use these devices with people. And we've hired grad students to do some crazy hand movement near the device, and we found that the recognition accuracy was pretty good. The reason for that is very simple, because the sensing range of our devices are basically 3 centimeters. Anything that is around 3 centimeters or beyond may not create enough light breakage to trigger our threshold algorithm. So we have implemented some applications. Nothing really fancy here, but just Yichen here is interacting with cat images and on the smart glass. And he's playing a video game by using the swipe gesture, middle finger gestures, and without touching the screen, which may cause occlusion. So here it comes to the end of this talk. I would like to wrap it up with some take-home messages. Well, the first, we've proposed and implemented a touch gesture detection and recognition method that does not really need an external battery. And we've run a number of studies to prove that this system is quite accurate in different lightning conditions. And we believe that this type of technology can be used in many power-constrained devices or even powerless device, batteryless devices, in IoTs and small wearable devices. And I want to take this an opportunity to acknowledge my co-authors again, and also NSF, which supports this research. If you look at the left side of this slide, Dartmouth Engineering is hiring at faculty and HCI. Please apply. All right, I want to thank you guys for your attention, and I'm willing to answer your questions.
Great, so ready to take some questions. Thad?
Hi, Thad Stoner, Georgia Tech. Love this stuff. Question is false positives per hour. So if you wore the glass device for an entire day, how many times does it false trigger as you go from indoors to outdoors and that sort of thing? Go through a doorway, that sort of.
So if just environmental light, it's not going to trigger. I would not say it's not going to trigger any, but I'm pretty positive, because if you go from indoor to outdoor, it's the global lightning change. That's something that our algorithm can take care of. As long as there's a small sort of a spot of changing light intensity, then we may think, the system may think it's
an easy test to do. I'd highly recommend doing it, because I would really kind of nail it in my book.
Thank you.
Great, thanks. Question in the back.
Dennis from University of Auckland. I actually had a kind of a similar question. So when you're walking outside, like conditions of course are changing. So does it mean your device is not working?
No, the device will work. Device will work. So if you think about it, if you
while you're walking, while you're walking, in the moment of walking.
Oh, the moment of walking. So basically, you switch from, let's say, a dark room to a bright outside patio. Is that right? So So your question is whether this is going to trigger any false positive.
In general, when you move, even in this room, the light conditions change all the time. It's different here, like some meters over there is different.
Yeah, so it's not going to work as long as a small part of the solar cells is triggered. Because if it's a global lightning change, it's not going to trigger anything, right? Because we have this algorithm to take care of that. If a small part of the solar cells detect as a big drop in energy, then it may trigger false positive.
Okay, thanks.
Okay, I think we have time for one more question, just for Roll.
Roll Vertical, Queen's University. Very nice work. I'm assuming there's no such thing as a transparent solar cell, because there has to be a photon-electron interaction, right?
Sorry, say it again?
There's no such thing as a transparent solar cell, right?
There's no such thing called a solar cell?
As a transparent...
and it's basically photodiode.
Yeah, so